Welcome to this workshop on online optimization. In this workshop, we'll demonstrate the way real-time optimization may be used in the powerhouse to minimize the cost of steam generation. For this workshop, we'll use an example of two boilers with different operating efficiencies. First, we'll show the impact of boiler efficiency on generation where the steam demand is a fairly constant value, and then the impact of cost when one boiler is offline. Then we'll look at the way steam is allocated between the two boilers as the steam demand changes. For this workshop, we have a dynamic simulation of two boilers, and one with different operating efficiency than the other. The steam generated by the boiler is going to turbines. This turbine extractions then is used to provide the processed steam to allow electric generation to be created to meet plant demand. Then there's a condensing turbine. Whether the steam demand is being met by the boiler is indicated by the header pressure that is used in the plant master to then change demand to the powerhouse. This is distributed through boiler masters to the individual boilers. The online optimizer then will be changing the bias to the boiler masters to shift the boiler load allocation to minimize overall generation cost. So in this workshop then, the optimization is being provided by an MPC with embedded optimization, where we're just using the optimizer part of the MPC, that is the linear programming that is embedded within the MPC. So this will be the basis for the optimization shown in this workshop. This is the interface to the simulation and to the optimization. As you can see through the interface, we can determine whether a boiler is online or offline. Also, there's the optimum cost associated, or optimum load to minimize cost. The constraints on steam and fuel generation are shown here. Also, the incremental cost of generation as represented by the change in tons per hour per unit of fuel input is shown and can be changed to demonstrate the impact of different boiler incremental operating efficiencies. The current steam and fuel demand is shown. The demand for steam from the plant master is shown here and can be changed, so we can look at the way the load is allocated for different loads to the boiler. The cost of steam generation is shown here, and to demonstrate the impact of the incremental efficiency on the steam cost and also the way load is distributed, we'll change that. And as you notice, the steam demand was shifted from boiler 1 to boiler 2 because our incremental efficiency on boiler 2 is now lower than the boiler 1. So this would give us the lowest cost of meeting our steam demand. Going back to our higher incremental efficiency, then you notice again the load is shifted from one boiler to the other. So in the shifting, rather than looking at actual efficiency, we're looking at the incremental change in efficiency and going with the higher incremental efficiency for adding steam or in terms of operation. By taking away one boiler, we can see the impact on the cost of steam generation. So we can see that with the lower efficiency, incremental efficiency, our cost is higher than it is with both boilers online. If we now put boiler 1 offline, the less efficient boiler, then we notice that when we do this, then the cost of steam generation is improved. That is, we're reducing the cost of steam generation by going with a boiler with the higher incremental efficiency in generation. So we'll now put both boilers online, and let's look at then the way steam is allocated as the load changes. We've seen what happens when one boiler is taken offline. That is, we're shifting the total demand to the boiler that's still online. So as we change the total steam demand to a very small number, we see that the total load is taken up by boiler 2, the one with the highest incremental efficiency. As the demand goes up, we still use the boiler with the highest incremental efficiency in terms of taking the total change in steam demand. But as the load is further increased above 200, we see that our constraint on the boiler operation comes into play. And so now then the remaining steam that can't be met within the limits of boiler 2 are now shifted to boiler 1. As a result of this optimization, we're able to minimize the overall steam generation cost independent of the steam demand. I hope this simple example will help you understand better the way online optimization can be used to minimize the cost of steam generation in Powerhouse, and can be used in other applications to minimize overall production cost within the plant.